Well, welcome to our third Thursday webinar. I am Tom Sandry, and today we are going to be talking about the importance of demagnetization of transformer cores. So, let's get started. Now, after a power or distribution transformer is disconnected from the power grid, or when a DC current is applied to it, for example, during a routine winding resistance measurement, the transformer core is likely to have some remnant magnetism. This remnant magnetism will generate high overcurrents when the transformer is re-energized, and this is commonly known as transformer inrush current. This inrush current, which runs for a few cycles, reaches a maximum when the polarity of the half cycle is the same as the polarity of the remnant magnetism and could damage the transformer itself or other components connected to it. Now, to avoid this undesirable effect, a transformer should be demagnetized after testing is complete and before being re-energized. Now, in this webinar, we're going to take a look at the magnetic circuits. We will talk about the BH magnetization curve, understand hysteresis, remnant magnetism, the effects of remnant magnetism, and demagnetization methods. Now, a magnetic circuit can be compared with an electric current in which EMF or voltage produces a current flow. The ampere turns, or the magnetic motive force, F sub m or MMF, will produce a magnetic flux, phi, as we see in this illustration. The MMF can be compared with EMF, and the flux, phi, can be compared to current. The equation shown is the mathematical representation of magnetic motive force derived using Ohm's law. Phi equals F sub m divided by R, which also equals MMF divided by R, where phi is the magnetic flux measured in Webers, F sub m is the magnetic motive force, or MMF, and ampere turns, and R is the reluctance, which is the ampere turns divided by Webers. Reluctance will be affected by the length of the coil, permeability of the magnetic material, and the cross-sectional area of the coil. Now let's take a look at the BH magnetization curve. The flux density, flux intensity, or BH magnetization curve shown here shows how much flux density B results from increasing the flux intensity H. The curves shown are for two types of soft iron cores plotted for typical values. The curve for soft iron 1 shows that flux density B increases rapidly with an increase in flux intensity H before the core saturates or develops a knee. Thereafter, an increase in flux intensity H has little or no effect on flux density B. Now, soft iron 2 needs much larger increase in flux intensity H before it reaches its saturation level at H equals 5,000 and B equals 0.3 T. Now, when current in a coil reverses direction thousands of times per second, hysteresis can cause considerable loss of energy. Hysteresis is defined as lagging behind. The magnetic flux in an iron core lags behind the magnetizing force. The hysteresis loop is a series of curves that shows the characteristics of a magnetic material as seen here. Opposite directions of current will result in opposite directions of flux intensity, shown as positive H and negative H. Opposite polarities are also shown for flux density as positive B or negative B. Current starts at the center, or zero, when unmagnetized. Positive H values increase B to the saturation point, or positive B sub max, as shown by the dashed line. Then H decreases to zero, but B drops to the value of B sub R due to the hysteresis. By reversing the original current, H now becomes negative. B drops to zero and continues to negative B max. As the negative H value decreases, less negative, B is reduced to negative B sub R when H is at zero. With a positive swing of current, H once again becomes positive, producing saturation at positive B sub max. The hysteresis loop is completed. The loop does not return to zero because of hysteresis. The value of positive B sub R or negative B sub R, which is the flux density remaining after the magnetizing force is zero, is called the retentivity of the magnetic material. The value of negative H sub C, which is the force that must be applied in the reverse direction to reduce flux density to zero, is called the coercive force of the material. The greater the area inside the hysteresis loop, the larger the hysteresis losses. A magnetic core of power transformers is found very often in a magnetized state. This magnetism is called remnant or residual magnetism, and it has undesirable effects on transformer operation. Now, there are several reasons that can cause remnant magnetism. When disconnecting a transformer from service, since the voltage is never in phase with the current and the current is interrupted at point zero, there is certain voltage at that point and corresponding flux would remain in the core at that point. The consequence of high fault currents that a transformer withstand, where relays cleared the fault, leaving some magnetism in the transformer core. DC testing. A winding resistance measurement on a power transformer is performed using DC current in the order of 10% rated current of the winding under test. Now, this test is normally performed as the very last test due to effects of remnants to other AC test results. Proper winding resistance technique to speed up the process of obtaining a stabilized result requires that the magnetic core be brought into saturation. Having DC current at that level makes the transformer core magnetized. Once the test is finished, switching current off, the winding is discharged, but it is not demagnetized. Now, remnant magnetism can cause various problems. Now, these problems include high amplitude of inrush current at startup, Now, inrush current is a form of overcurrent that occurs during energization of a transformer and is a large transient current which is caused by part cycle saturation of the magnetic core of the transformer. Now, when an electric power transformer is switched on from its primary side with keeping its secondary circuit open, it acts as a simple inductance. When an electric power transformer runs normally, the flux produced in the core is in quadrature with the applied voltage as shown in the figure. That means the flux wave will reach its maximum value 1/4 cycle after the voltage wave reaches maximum value. Hence, as per the wave shown in the figure, at the instant when the voltage is 0, the corresponding steady-state value of flux should be at negative maximum. But practically, it is not possible to have flux at the instant of switching on the supply of the transformer. This is because there will be no flux linked to the core prior to switching on the supply. The steady state value of flux will only be reached after a finite time, depending upon how fast the circuit can take energy. This is because the rate of energy transfer to a circuit cannot be infinity. So, the flux wave will be initiated from the same origin as the voltage waveform at the time of switching on the transformer. Now, transformer cores are generally saturated just above the maximum steady state value of flux. But during switching the transformer on, the maximum value of flux will jump to double of its steady state maximum value. After the steady state maximum value of flux, the core becomes saturated, and the current required to produce the rest of the flux will be very high. So the transformer primary will draw a very high peak current from the source, which is called the magnetizing inrush current in a transformer, or simply the inrush current in a transformer. Now, if during re-energizing the initial value of flux differs from the prospective flux due to remnant magnetism, a DC offset of the flux linkage will be caused, and a higher than rated peak value will be present. This results in an inrush current that may be several times the value of the normal current. So, let's now look at the effect of remnant magnetism. First, let's look at mechanical damage. Mechanical damage to transformers' active parts. The windings are exposed to mechanical stress proportional to the square of the current. Mechanical shocks caused by overcurrent surges may damage the coils and release the clamping pressure. This would eventually lead to loose windings of a transformer and possible transformer failure. Also, the effects of remnant magnetism can cause power quality problems. Power quality problems may arise due to remnant magnetism at time of startup. If remnants is present, high resonant harmonic overvoltages and voltage sags are all present when the transformer operates in the first few cycles after the energization. Effects of remnant magnetism can also cause incorrect operation of protective relays. The protective device for overloads and internal faults may falsely operate and disconnect the transformer from the electric system. The figure here shows a saturation where the inrush current was switched off after 5 cycles of transformer energization. The A-phase current exceeded 400 amps in the first half cycle, while the other 2 phases show great symmetry, presence of higher harmonics in the current waveform. The consequence of this unnecessary relay operation is the need for another subsequent powering of a transformer, introducing another mechanical shock to the unit. Now, another effect of remnant magnetism is incorrect diagnosis of test results on the transformer. Now, in the event of a fault or during routine tests, various electrical diagnostic techniques can be used for analyzing the condition of a transformer. Residual magnetism influences certain diagnostic measurements in such a way that a reliable and meaningful analysis becomes nearly impossible, particularly when performing excitation current measurements or sweep frequency response analysis for localizing of faults in the core. Residual magnetism may have such a negative effect that the test results become unsolvable and useless. The direct current used to measure winding resistance may cause the core to magnetize. As we discussed, a magnetized core can cause high inrush currents when the transformer is energized or can cause incorrect diagnostic test results. To help reduce damage to the transformer and associated protection systems, the core may be demagnetized prior to applying full alternating current or AC voltage. Now, one of the influences of remnant magnetism is on excitation current measurements. Measuring the excitation current can provide evidence for potential faults in the core. Faults in the core lead to an increasing excitation current. If reference values for the exciting current are available, these can be used for the assessment. Now, since exciting currents do not have a linear behavior to the applied voltage, measurements for comparison with the reference values must be performed at the same voltage. The assessment is performed based on a typical pattern of a 3-limb or 5-limb transformer or based on reference measurements if they are available. The magnitude of the magnetization current depends on the length of the magnetized path. This is virtually identical for the windings on the outer limbs, but lower for the windings on the middle limb. If there is, for example, residual magnetism on the middle limb, this can easily lead to incorrect interpretation and a reliable diagnosis becomes impossible. Now, the currents measured on a 3-phase unit will show a pattern across the phases. Typical patterns that we would see would be a high, low, high value or a low, high, low value. The presence of remnant magnetism can skew these results, and we might end up with an unrecognized pattern such as a high, medium, low value of reading. Next, let's talk about the effects of remnant magnetism on sweep frequency response analysis. The sweep frequency response analysis, or SFRA, uses frequency response analysis, FRA, to describe the dynamic characteristics of an oscillating network based on its input and output signals. The SFRA measurement method is described in IEEE C57.149 and becomes increasingly accepted as a diagnostic test method for transformers. A transformer contains an oscillating system consisting of various series and parallel resonances with corresponding inductances, capacitances, and resistances. When one parameter is changed, for example, the main inductance due to a core problem or the geometric shift of a winding, one or more characteristic resonant points is or are also displaced or shifted. Every electrical network or transformer has a unique frequency response, its so-called fingerprint. Interpretation of an SFRA measurement is based on comparison of measurements, for example, with the initial fingerprint or with other transformers of the same type. The plot of a fingerprint should not change throughout the entire life cycle of a transformer. All influences which could affect SFRA measurements must therefore be avoided, and they could lead to misinterpretation of the obtained test results. Now, the SFRA measurement reflects the main inductance through the first resonant point. The FRA signature shown here shows the typical resonance point of a three-limb transformer's main inductance. Two significant parallel and series resonant points can clearly be seen on the outer windings. This can be attributed to the two magnetic paths with different lengths. Here we see the first resonance and equivalent magnetic path. And here we see the second. In comparison with this, the winding on the middle limb displays only one characteristic single resonant point. Now, as previously explained, for the inrush current, the inductance changes depending on the degree of core magnetization, whereby inductance demag is greater than inductance magnetized. A resonance point comprises a network of capacitances and inductances. The lower the inductance becomes, as reflected by a state of higher residual magnetism, the more the resonant point moves toward the higher frequencies. Here we see the shifting of the resonance of the C phase toward 1 kHz. We also see less magnitude on the first resonance of the C phase due to reduced inductance caused by residual magnetism. All right, now let's talk a little bit about demagnetization methods. Removal of remnant magnetism during startup will extend transformer life by avoiding unnecessary stresses during startup. Also, the removal of remnant magnetism prior to condition assessment tests will render more reliable test results. Therefore, we will discuss 3 methods for removal of remnant magnetism from power transformers. We will talk about the variable voltage constant frequency source method, the constant alternating voltage with decreasing time method, and finally, the decreasing amplitude of an alternating polarity DC current method. Now, the variable voltage constant frequency source is the best method performed in the factory and requires a very large energy source. Now, it isn't practical for field operation because it requires a power frequency, 50-60 Hz, source powerful enough to magnetize the magnetic core. Now, another requirement is the ability to control and slowly reduce the applied voltage. By reducing the voltage and current from operating levels down to 0, the core is demagnetized. However, this is impossible to do in the field on even a medium-sized power transformer due to the very large VA requirements of the test set. Now, the old IEEE Standard 62, Section 6.1.3.5, directs one to alternate the polarity of a fixed voltage with decreasing application time per alteration of polarity. Now, this is the constant alternating voltage with decreasing time method. The principle of this method is to neutralize the magnetic alignment of the core iron by applying a direct voltage of alternating polarities to the transformer winding for decreasing intervals. The interval is usually determined when the demagnetizing current reaches a level slightly lower than the previous level, at which time the polarity of the voltage is reversed. The process is continued until the current level is zero. On three-phase transformers, the usual practice is to perform the procedure on the phase with the highest exciting current reading. In most cases, experience has demonstrated that the procedure is sufficient to demagnetize the whole core. Now, the explanation is clear. With decreasing time, you should obtain slightly lower magnitude of the current. However, this is easier said than done. Once the current reaches the knee point of the saturation curve with applied fixed voltage, it changes too fast to manually control with precision. Experience has shown that improper procedure will very often cause other core legs to get magnetized while one is being demagnetized. Now, shown here, proper time sequence for diminishing current magnitude should be at the first sequence reaching the amplitude of 25 amps at 55, 53, 50, 45, 41, 38 seconds. Not to mention that at lower current levels, we may be talking fractions of a second. Now, the IEEE standard C57.152 that has superseded IEEE 62 states that a more convenient method of demagnetization is to use direct current. Modern electronically controlled DC instruments can control the amplitude of the applied current with very high precision. Applying the decreasing amplitude of an alternating polarity DC current method, they can be programmed to perform polarity reversal and automatic demagnetization of the power transformer magnetic core. Now, this method is the engineering approach to the IEEE standard directive to alternate polarity and lower the flux in the magnetic core by controlling the current amplitude in each step. The value of the initial amplitude is not important as long as saturation is reached on all three legs of the magnetic core. Following initial current charging and discharging, the next alteration is of 50% magnitude, and when reached, discharge is initiated, and the steps go on in succession until the very small value of ampere turns is applied at the very last step. So, let's review. Several reasons may cause remnant magnetism. Disconnecting a transformer from service. Clearing high fault currents. DC testing, such as the winding resistance test. Remnant magnetism can cause various problems. A high amplitude of inrush current at startup. Mechanical damage to the transformer's active parts. It can cause power quality problems, and also causing the incorrect operation of protective relays. Also, it can cause incorrect diagnostic test results. Now, there are effective ways to remove remnant magnetism. The variable voltage constant frequency source, which is preferred at the factory. The constant alternating voltage with decreasing time, which can be a bit impractical and difficult to perform properly. And possibly the field preferred method, the decreasing amplitude of an alternating polarity DC current method, which many of the new modern test and measurement equipment have the capability of performing, particularly in many of the new winding resistance test sets. Now, the removal of remnant magnetism during startup will extend transformer life by avoiding unnecessary stresses during the startup, and removal of remnant magnetism prior to condition assessment tests will render more reliable test results. And that concludes our webinar today on the importance of demagnetization of transformer cores. I thank you, as always, for your attendance in these webinars. We always love looking at the attendance list and seeing a lot of our friends returning month after month. Again, I truly do hope that these are of value to you. We do enjoy putting them on. So let's get to those questions and answers.